In this video, we're going to look at how to represent potential energy graphically using the rather aptly named potential energy diagrams. So this diagram here is the diagram that we use to represent exothermic reactions. Let's just choose one of the more well-known exothermic reactions that exist. C6H12O6 is the chemical formula for glucose, where if we burn glucose in the presence of 6 oxygen molecules, we get 6 carbon dioxide and 6 water molecules. And of course, since this is the reaction we use to produce energy for our bodies, we know that delta H is going to be a product because this reaction releases energy here. Now, in terms of what this graph here represents, we'll know more when we put the variables on the appropriate axes. So potential energy is written on the y-axis, usually with the measurement kilojoules, and then some version of the passage of time is represented on the x-axis. You can also write the word reaction progress or something to that effect if you want to show the passage of time without specific intervals of time referenced here. Now, in order for us to make sense of this graph here, we can recall the formula for delta H, in which delta H is the sum of the potential energy of our product molecules, and we're going to subtract the potential energy of the reactant molecules here. Now, on our potential energy graph, this constant level on the graph represents the potential energy of the reactants before the reaction takes place. Here's where the reaction begins to occur, and here is when the reaction is complete, and where we have the products here. Now, remember that delta H being in the products means that delta H is going to be negative, and using this graph, we can see why. So here, we can see that the potential energy of the products is clearly less than the potential energy of the reactants. And then if we refer back to our formula for delta H, if the potential energy of products is less than the potential energy of our reactants, when we use the formula for delta H of products minus reactants, we are going to get a negative number here. This is why delta H is defined as being negative for an exothermic reaction, because if we know that the products have less potential energy than the reactants do, that must mean that the delta H formula will give us a negative number, because a smaller number subtracting a bigger number from it is going to be a negative number. Now, if we consider an endothermic reaction, all that we need to do to find an example endothermic reaction is just to flip cellular respiration around. So biology students again will know that 6 carbon dioxide and 6 water can combine together in the presence of energy, which plants get from sunlight, in order to allow them to produce sugar and the oxygen gas that all organisms depend on for breathing. So here, we can see that this is an endothermic reaction because delta H appears in the reactants here, which means that energy is absorbed by this reaction, and carbon dioxide and water use that energy to combine together in order for plants to produce sugar. So if we, again, label our potential energy curve with all of the relevant variables, so potential energy on the y-axis and then time on the x-axis here, we can see that our graph is basically the mirror image of the exothermic graph, because if our reactants are here and our products are here, if we compare their potential energy, the potential energy of the products this time is actually greater than the potential energy of our reactants. And therefore, if we refer back to our formula for delta H, if we take a greater number and subtract a smaller number from that, we know that delta H is going to be positive, because again, taking a bigger number and subtracting a smaller number based on the formula, this allows us to see why endothermic reactions have a positive delta H. In the next video, we're going to explore a little bit in more detail what happens when you take an exothermic reaction and flip it around in order to make an endothermic reaction, and what that means in terms of the magnitude of the delta H of that reaction.